In this video, you're going to learn about the second set of problems regarding stress strain. A sculpture weighing 10,000 newtons rests on a horizontal surface at the top of a 6-meter tall vertical pillar. The pillar's cross-sectional area is 0.20 meters squared, and it is made of granite and a mass density of 2,700 kilogram per cubic meters. Find the compressive stress at the cross-section located 3 meters below the top of the pillar and the value of the compressive strain at the top of 3.0-meter segment of the pillar. As we proceed with the diagram, we are given with this sculpture which sits atop a pillar. The area now is 0.20 meters squared, and then the weight of the sculpture is equal to 10,000 newtons. Then the height, okay, is equal to 6 meters. The density is equal to 2,700 kilogram per cubic meters. And then additional given is the bulk modulus for your granite at 4.5 times 10 raised to 10 pascals. Okay. We're going to label the diagram, the weight of the sculpture, okay, and the weight of the pillar points downward. Then remember that the weight of the sculpture is equal to 10,000 newtons. We are required to solve first for this stress. Okay? Find the compressive stress at the cross-section located 3 meters below the top of the pillar. Okay? And then the second one is we're going to solve for the strain at the 3.0 meter segment of the pillar. Let's proceed with the solution. So the first one is to determine the volume, mass, weight of the pillar segment. The volume of the pillar now is equal to as the cross-sectional area multiplied with the height. Okay? We're not going to use the height at 6 meters. On the problem, it is stated that the analysis will be taken 3 meters, okay? 3 meters below the top of the pillar. So we're going to consider the height at 3 meters. Now, if we're going to calculate the volume of the pillar, this gives us V is equal to A times H. Okay? So we are given with the cross-sectional area of the pillar at 0.20 meters squared. Multiply it with the height of analysis at 3 meters. This gives us a value of 0.6 cubic meters. Then the mass of the pillar is calculated with respect to the volume and the density. Okay? Now, our density for the granite is given as 2.7 times 10 raised to 3 or 2,700 kilograms per cubic meter. Multiply it with the calculated volume at 0.6 cubic meters. Okay? Further simplifying this as your cubic meter units cancels out, this gives us 1.6 times 10 raised to 3 kilograms. Now, if we're going to calculate the weight of the pillar, this gives us WP, okay, which stands for the weight of the pillar. It is equal to the mass times gravity. Okay? The mass now is equal to 1.6 times 10 raised to 3 kilograms. Multiply it with the gravitational constant at the Earth at 9.8 meters per second squared. Further simplifying the following values gives us 1.57 times 10 raised to 4 newtons. Okay. The second set of the solution is to determine the whole force, which is the sum of the weight of the sculpture and the pillar. Okay. At the bottom part of this one, the force now is equal to the weight of the pillar plus the weight of the sculpture. Okay. The force now is represented as F be equal to Ws plus Wp, representing the weight of the sculpture and weight of the pillar. Okay. As we substitute the following values, 10,000 newtons for the weight of the sculpture, plus the solved value for the weight of the pillar at 1.568 times 10 raised to 4 newtons, okay, or 15,680 newtons. If we're going to add up the following values, this gives us 25,680 newtons. Now, let's proceed with the objective of the problem. For the first one is the stress, okay? Stress at the cross section located 3 meters below at the top of the pillar, okay? Stress now is equal to sigma is equal to the force all over area, okay? The total force now is equal to 25,680 newtons all over the cross-sectional area at 0.20 meters squared. Further simplifying the following quantities gives us 128,400 pascals or 128.4 kilopascals. And for the strain, epsilon is equal to your stress sigma all over your Young's modulus. So this is equal to 128,400 pascals over 4.5 times 10 raised to 10 pascals. Further simplifying it to the following values, which is equal to 2.85 times 10 raised to negative 6. Okay? This is unitless because both Pascal units for numerator and denominator cancels out. So that ends my presentation for the second set of the problems. For my next video, we're going to talk about shear and bulk modulus. Shear deformation and bulk deformation.